Okay, welcome everyone. Today we are happy to have Mikhail from MIT. He's going to tell us how to understand tides with scattering amplitudes.
Thank you. Yeah, thank you so much for having me here. It's a great pleasure to be here. So I'm going to present some work that has been in progress with all these collaborators that you can see, and let me specifically emphasize my junior collaborators, student Zikan Zhou and postdoc Yu Zhou Li, who did most of the heavy lifting for this work. In general, I work at the interface between theory, mostly effective field theory, and data analysis in order to test new physics. And there are two general examples of this research program. So one of them is my group's work in cosmology, where we use effective field theory for large-scale structure and effective field theory for inflation to interpret data from galaxy surveys and then extract new information on new physics, on the physics of dark matter, dark energy, inflation, neutrino masses. And then also another example of my work at the interface of EFT and data analysis is the work on EFT for gravitational waves, where I'm using a combination of theoretical tools such as the EFT for binaries and scattering amplitudes, also in combination with more classical methods such as black hole perturbation theory and jar calculations, again, in order to understand better the general structure of general relativity and to streamline the analysis of data from the gravitational wave experiments such as LIGO, KAGRA, and Virgo. And in my talk, I'm going to specifically present some results from this research program that will culminate in the new constraints on exotic compact objects and test of GR from the gravitational wave data. But if you have any questions about cosmology, I'm staying here today the whole day, so I'll be very happy to chat about cosmology as well. All right, so this talk will be about the gravitational waves. And right now we have around 100 different gravitational wave events that have been accumulated over the last 10 years. And this remarkable experimental achievement also triggers also poses some of the theoretical questions. And the most pressing one is the precision waveform calculations from the theory point of view that are badly needed in order to interpret the data. And in my work, I'm going to show you the application of different theoretical tools, effective field theory, black hole perturbation theory, and scattering amplitudes that ultimately I'm going to apply to the data I'm going to use to understand better the gravitational wave observables. In general, a typical binary merger consists of three phases. You have the inspiral phase, then the coalescence, and the ring down phase after that. And three different phases. They're sensitive to very different physics. So during the inspiral phase, the typical situation that takes place is that you have two compact objects that tidally perturb each other. And in this case, you're sensitive specifically to the internal structure of those bodies. And for instance, on the other part of the spectrum, in terms of the time space, we have the ring down, which describes the quasi-normal modes of a black hole that corresponds to a totally different physics. This is something that will tell us maybe if the black holes that we observe, they really match GR or not. But in general, these different phases, they allow you to probe different physics, and also we use different tools to describe them. In my talk, I'm going to mostly use the inspiral phase right here, and I'm going to focus specifically on the question of tidal deformations of the sources of gravitational waves, because this question is, the question is why we can probe the internal structure of gravitational waves, given that the wavelength on gravitational waves is much bigger than the size of the object. So it's a very non-trivial question if you think about this, right? Because when the LIGO announced their results, everyone believed that it's a black hole, but actually, what was the main motivation to believe that it's a black hole? Which, it's not obvious at the beginning that you're sensitive to the internal structure. And in fact, you are sensitive, even if the gravitational wavelength, which scales like the orbital size divided by the orbital velocity, even if this parameter is much bigger than the size of a compact body, still there will be some effects due to the finite size imprinted in terms of the multipole expansion, so imprinted in terms of the finite size effects. So those are the effects that I'm going to discuss today. And in general, there are two classes of the finite size effects. The first one is the tidal dissipation, which is responsible for the effect called the tidal locking. For instance, takes place in the Earth-Moon system. So we know that the Moon is always looking at us with the just one side. So this is the result of the tidal dissipation. So the absorption of the mechanical energy and transforming this into heat. And in general, this is the 2.5 post-Newtonian effect. So it enters the gravitational waveforms pretty early. So you can see some dephasing already at the very early stages of the spiral. And then there is another tidal effect, which is of conservative nature, which is a tidal deformation, where really the surface of the compact bodies are getting deformed. And this is something that is described by the so-called Love numbers. So in general, this is an effect that scales in the post-Newtonian nomenclature as a 5pn effect. And this leads to dephasing, well, at high, let's say, at high frequencies later on before the merger. And in principle, using these two effects, we can say something about the structure, the internal structure of compact bodies. So for instance, there is a very significant effort to understand the equation of state of neutron stars by using specifically the conservative deformations. So in my talk, I'm also going to present some of the results on the specifically using the tidal heating to describe the internal structure of gravitating bodies.
So this PM, what is 2.5 post-Newtonian? What is?
Yeah, so PM is a scaling, is a expansion in terms of the velocity squared. And typically when you have dissipative effects, the dissipative effects, they don't respect the time reversal symmetry. So they scale like just velocity, the odd power of the velocity. So 2.5 means, well, basically V squared to the 2.5, right? So this would be V to the 5 effect, and this will be V to the 10 effect, where V is the, well, I'm using the units where C is equal to 1. So here we're talking about V over C, to the 10th power, where V is the orbital velocity. So you see, it's a very subtle effect for most of the part of the spiral evolution.
What's the experimental bound on how high you can go in PPM detected? I mean, effects at what order can actually be seen?
So, okay, the actual statement really depends on the compact object. The standard kind of number that we always use is 5 post-Newtonian. We're sensitive to everything at up to 5 post-Newtonian, but in fact, it could be sensitive to something that scales more than that. Well, for instance, in the case of Love numbers of neutron stars, which I'm showing here, they could be additionally enhanced because they scale, well, their effect is enhanced by the ratio of the radius with respect to Schwarzschild radius. And the radius could be big, so this will additionally enhance the effects, even though they scale formally, 5 post-Newtonian, there will be an additional boost due to the size of the compact body. So,
what about within the solar system? How sensitive are we?
Well, for instance, we're super sensitive. Well, for instance, even for asteroids, we can measure Love numbers with like very tiny precision, but we're not using gravitational waves for that, right? So specifically here, gravitational waves is a very subtle effect, but in principle, tidal deformation is something that you can measure using other probes. So here in this plot, I'm showing you some of the results of this program implemented by the LIGO Virgo KAGRA collaboration, where you can see some constraints on the tidal deformabilities, the Love numbers of neutron stars from the GW 170817. And well, here you can see that, well, this is the maximum likelihood point, and then this maximum likelihood already rules out some of the equations of state. So this is how in practice this program works. But however, now let me give you a more concrete definition of what are the tidal effects and how we're measuring them with gravitational waves.
Sorry, can you go back about just the previous slide?
Yeah.
How are they actually asserting they're looking at neutron stars?
Yeah.
I mean, what's the evidence? Is there evidence beyond gravity waves? Are they looking at other signatures or?
Well,
as opposed to
you mean the equation of state? Yeah, people use other observations, but in general, it's harder. Like this, if you want to study the equation of state, the tidal information, you need another compact body. So in general, this is a better test of the equation of state of neutron stars than anything else, because these Love numbers, they're really sensitive to the internal structure, right? Because there are many other observations.
The question is, how does LIGO know it's a neutron star?
Oh, well, for instance, for this particular event, there was a follow-up in terms of usual light.
Okay, so
right?
an optical signature or something.
Yeah, but also you can measure the masses, and if the masses are below the Volkoff-Oppenheimer limit, which is roughly 3.5 solar masses, then probably it's a neutron star. So it's a combination of two things always. That this is something that has tidal deformations, and for black holes, as I'm going to say in a moment, so they have zero tidal deformations, at least in order. So this is the first piece of evidence. The second piece of evidence is the masses. And third piece of evidence is the light that you can get from an optical, let's say, follow-up another in the electromagnetic part of the spectrum, basically.
Good. Okay.
Cool. All right. So these love numbers that I mentioned before, they were introduced by a British mathematician Love more than 100 years ago, and he considered a very simple problem. So we have a compact fluid body. In the absence of any external forces, this fluid body would assume a spherical form. Now imagine that there is some tiny perturbation, like a satellite, and this satellite then exerts a tidal force, and in response to this tidal force, the central body will deform, and this deformation will produce multiple moments. So in the absence of any deformations, you will have just a monopole. Now with the deformations, you will generate whole tower of multiples. Well, the first non-trivial one being the quadrupole moment. So now the total, let's say, quadrupolar part of the potential will have the tidal force and the tidal response. And then you can generalize this construction to any multipolar order, to higher orders. And basically what Love assumed, which was very natural, is that in linear response theory, the amount of the tidal deformation will be linearly proportional to the amount of the tidal force from the source. And the coefficient of the proportionality between them is called the Love number. So this concept can be generalized to higher orders, let's say, in the frequency of the perturbation. So in principle, you can think about, in linear response theory, you can think about the Love number as something that has dependence on the frequency of the source. In general, there is an expansion in terms of the omega, well, which is the frequency times, just by dimensional analysis, some typical size of the compact body. And then the even powers, they will capture the conservative part of the response, and the odd powers will capture the dissipative part of the response. And it's very similar to the polarizability expansion and linear response theory and electrodynamics, where again for the polarizability, we know that the even powers, they capture the material deformations, or for instance, they're responsible for reflection of light, and the odd powers, they capture really the absorption of waves. All right, but since I started my talk about discussing really the gravitational waves and full-fledged GR, so you might have some issues with the definition of the Love numbers in the case of general relativity. So ideally, we want to extrapolate the notion of Love numbers to that case, and we want to have a definition that matches the Newtonian one at large distances, but that the definition is also invariant with respect to the symmetries of GR. So it has the reparametrization variance and diff invariance. Then you might have some more conceptual questions. For instance, we know that GR is very nonlinear. And before I was talking about this story about the source and response, which is extremely linear. So does this split mean actually, well, does it make any sense in GR? So this is a very natural question. Well, the spoiler, no, like this is something that we'll certainly will have to modify. And the way to generalize the notion of Love numbers in general is to use the so-called worldline effective field theory suggested by Walter Goldberger and Ira Rothstein. So let me walk you through this worldline EFT construction. So basically, the general idea of the gravitational wave astronomy is that we need to solve a two-body problem in full GR, including the radiation, which is extremely hard. And the idea now is to split this problem into different domains and build up a perturbative expansion within each domain. And in principle, you can separate three domains. So the first domain is the one-body sector, where you build an EFT for compact objects themselves, for the gravitational potential of the compact objects. And the typical scale associated with that is the size of the compact body, which roughly is given by the Schwarzschild radius. And then the second domain is the domain of the potential motion. So those are the near zone of the binary. And the third domain is the domain of the radiation itself, where the typical, well, we're talking about the frequency of the gravitational waves. So those are the typical degrees of freedom that we keep. And well, typically the wavelength of the gravitational wave is much bigger than the orbital radius. So you have this nice scale separation. In every domain, we take advantage of the scale separation and we build EFT as a power series in terms of the distance expansion, gradient expansion. For the first part of my talk, let me focus on this part, the EFT description of the compact bodies themselves. And in that case, the idea of the point particle effective field theory for compact bodies is that from far away, every compact body just looks like a point source. So for any compact body, we can just write down this point particle action. And then the finite size effects are described as higher order operators that we put on the worldline. Maybe as a warm-up, we can go through the example of the worldline effective field theory for the electromagnetic radiation. So again, if we're talking about the external electromagnetic fields, whose wavelength is much bigger than the size of our object, charge distribution, then we can work out multiple expansion, and basically EFT is the way to generate the multiple expansion. So we can replace this picture, we can replace our charge distribution with just a bunch of multiples, and then we can write down an effective field theory where we couple the degrees of freedom of the external fields to the worldline degrees of freedom. And at first order, of course, we can write down the usual point charge action. Then the next to the order operator, the one that is consistent with all the symmetries, will look like this. Will involve the square of the Maxwell tensor. And in the body's rest frame, this is something that reduces to the square of the electric field seen by the worldline. And the coefficient that appears here in front of this higher order operator, it scales like distance cube. And this is something that, it's in principle, as you can see, this EFT involves the irrelevant operators. So it's higher order operators. And the expansion is naturally organized in powers of distance from here. And the sky that appears here will be precisely the polarizability of the compact body. And we can carry out a simple response calculation to make sure that this is indeed the case. So if I focus only on the neutral particles, so the charge is 0, so my worldline action will start with this term that involves the electric field squared, and then I can also add the Maxwell field in the bulk. And then I can say that my total electric field consists of some source and some response contribution. So I plug this decomposition in my effective action. It will solve the equation of motions perturbatively. And I find that the total field now will look like the source minus some contribution from this effective operator over r to the cube. And this is something that we can easily identify with the effect of the induced dipole moment. So in fact, now this effective action just describes the appearance of the usual dipole polarizability. So chi is just the usual polarizability coefficient. Okay, so this is how this EFT works. I mean, obviously for E&M, we don't need the EFT because we can solve everything using the classical methods. So this description is totally redundant, but it becomes really useful when we talk about gravity, because in gravity we cannot find the exact solution otherwise. To include gravity, basically what we have to do is to repeat this calculation, but now for the metric degrees of freedom. So again, from far away, everything will look like a point source, and then you can show that the first non-trivial higher order worldline operator will be the square of the gravielectric field, which is basically the Raman tensor contracted with some 4 velocities. And this is something that in the Newtonian limit reduces to the usual tidal field. So basically what we're going to get at large distances is that we have the higher order or higher derivative theory of the scalar field, where scalar field is your Newtonian potential. Just because of this reduction at large distances, it's also often useful to talk about the scalar, for example, the scalar EFT, because it kind of matches gravity in the large distance limit. Okay, but in general, you see the idea is very simple. I just write down all possible worldline operators and see what's going to happen. And with these worldline operators, now we can again do the same kind of response calculation as we did before in the case of the electromagnetic radiation. And now again, we can say that we have some gravitational potential far away that is produced by some source, and we can calculate the response to this gravitational potential by the worldline, and we're going to find a contribution that will scale exactly like the induced multiple moment. And now you can see that the Wilson coefficients that appear here in this effective action, they precisely match the low numbers at large distances. So you see that indeed the definition of the tidal deformability with the EFT is something that does reproduce the usual notion of Newtonian law of numbers at large distances, but then respects all symmetries of GR, because again, we started with the fully covariant action here.
So with this, the assumption is pure gravity, no extra fields in the story.
Yeah, pure gravity. I mean, you can also do just electromagnetic field if you want to describe electromagnetic response. Yeah. All right, so we have obtained this kind of interesting EFT for which the actual general relativity is a full UV theory. So our EFT is valid at distances larger than the shortest radius. And then if we want to obtain the Wilson coefficients, we need to match it to some jar calculations. And for instance, now we can carry out this response calculation. So we can compute the expectation value of the one-point function in particular frame, local asymptotic rest frame, and we can find the correction to the, let's say, Newtonian potential. And then we can, in the EFT, and we can also carry out these calculations in GR, and we match the two, and this is how we determine the log number. And the power of the EFT is that it doesn't matter, whichever means you can use to extract the log number. Then once you have it, you can make new predictions for new observables. EFT will always guarantee that the same number will appear in other calculations, in other observables. So in terms of the log numbers of black holes, however, there was always some ambiguity, and always there was some sort of back and forth with the calculations of the log numbers. And this is because, again, even if you compute the one-point function in some frame, this definition is still coordinate dependent. And this is something that kind of plagues the calculation of the off-shell observables, such as the gravitational potential. And well, in fact, EFT in this regime kind of just reproduces what people would have done anyway. So the GR people would just say that we should usually split into the growing and decaying tail, and the coefficient from the decaying tail will be a log number. So in this sense, it's kind of the same. And the problem is really to match it to other off-shell calculation that is carried out in some particular gauge, in some particular coordinates. And this was always, problematic. Even at the very beginning, when people realized that it would be good to compute the log numbers, there was some back and forth. But then after some papers, people, when they aligned all the gauges, they were able to show that the log numbers, static log numbers of black holes are 0. Then when they sort of increased the level of complexity and started talking about the log numbers of the KAGRA black holes, again, there was some confusion. And again, the problem was that different results obtained with different prescription coordinates that were given different answers. Or for instance, first there was a claim by Utek and Casals that the log numbers of KAGRA black holes are non-zero. But this is because basically at the level of the KAGRA black holes, we have a mixing of dissipative and conservative effects. And well, it's hard to disentangle them if you don't use the EFT. So then there were some papers, including our paper using the EFT, where we show that actually, if you account for dissipation, then you can show that the log numbers is 0. But in general, it just tells you that this matching in terms of the off-shell observables is always very tricky. And the new frontier now is to match the next to in order log number, the so-called dynamical log number that corresponds to the omega square correction to the usual log number. So this corresponds to the response term that has the tidal field with 2 derivatives. And again, there are some very nice jar calculations carried out in particular gauges that say that the dynamical log number is 0. But then, well, I carried out some calculations that show that actually it's not 0. And it's very hard to reconcile these calculations. Conceptually, the problem is that what happens here is that really you start being sensitive to the relativistic corrections of GR. So the relativistic corrections to the source term in your source response expansion, they start scaling the same, producing the terms that scale the same as the log number itself. So, well, in the QFT language, there are loop diagrams that produce the running of the log number. So this is something that again produces a lot of confusion.
Sorry, can you explain that? I thought we're doing classical field theory here. What are the loops? What are you integrating?
And these are classical loops. Yeah, because whenever you have perturbation theory and some ensemble average, this will generate Feynman diagrams and loops, even
Why do we
for
have an
classical.
ensemble average?
Well, in this case, you can think about this ensemble average over different short scale modes, right? So we're integrating out.
Why
in
are
terms
we
of-
integrating something out?
Oh, because we don't know, we have some compact body, we don't know what's inside it. We're integrating out their modes, right? So this integrating out generates the ensemble, right? And this is something that then produces the same thing in the knowledge or produces the same machinery as what we normally have with Feynman diagrams. Yeah, so all the calculations here are classical. You can think about them as follows. You can treat gravity as an effective field theory, and you can start computing, for instance, the effective potential, of the exchange. You have, let's say, two scalar fields, they scatter. If you do tree-level diagram, this computes the Newtonian potential. If you start like putting a loops, this will compute both the classical the classical relativistic correction to the Newtonian potential, and also the quantum corrections, right? You compute. Well, there are different types of loops that are responsible for quantum or classical effects, but with the Feynman diagrams, you can compute classical nonlinearity as well. So this is what I'm doing here. So there is a classical nonlinear, there's a classical 5-loop diagram that produces the running of the log number. Okay. So for me, this was more an example, motivation that somehow we have to start thinking about these things differently. As matching the EFT calculations becomes more and more hard at higher post-Newtonian orders, it would be good maybe to come up with a different approach, because given this example of the dynamical of numbers, it's not easy for us to say whether we need to include the dynamical of number in the waveforms or not, right? Because there are two calculations, different gauges, giving you different answers. Now, what will you use for the waveform? And yes.
These are fortunately two side questions, maybe better for later, but in the Kerr case, as you approach extremal, is there any subtlety in the breakdown of the EFT?
No.
I believe to be a problem there.
No.
For the charge case,
Yeah.
is if I take a charge black hole, is it still true the log number is 0?
Yeah, it's still 0. Yeah.
Still 0.
Still 0. Yeah, in 4 dimensions, all log numbers are 0. Oh, except for the dynamical ones. Dynamical are not 0.
So someone must have looked at this. So this is again a little bit of an aside, but in string theory, there's a claim that you can have very close to black hole-like solutions, which are just complicated stars, puzzles of one kind. Do they have log numbers which are?
Yeah, they will have log numbers. Yeah.
They will have, okay, so
Yeah,
it's
yeah.
not very small.
If something is not exactly black hole, it will have log numbers. Yeah. All right. So okay. Then here in this slide, what I wanted to tell you as a result of this discussion is that not only do we have to use EFT to define tidal effects, but also we have to use scattering amplitudes to actually match the Wilson coefficients, because this is the only kind of alternative which is very clean and that allows you to perform this matching in a very on-shell way that is gauge invariant, that doesn't depend on the parameterization on the fields that you use. So it's a very clean way to really extract these Wilson coefficients. And again, you can match them from some simple calculation, and once you have the matching, you can then use them to make predictions for the gravitational waveforms. So you can think about this program as a streamlined approach to make predictions for gravitational wave experiments. So let's
Before you go on,
yeah.
Can we go back a couple
Sure.
slides? I kind of didn't understand the punchline here. So
Okay.
are the log numbers well defined?
Yes, they
So
are
what is
well-defined.
going on with the logs then?
The log numbers run.
The log numbers run?
Yeah.
Okay, so
Just like any coefficient in quantum mechanics. Yeah, they run, and this kind of diagrams induce the running of log numbers. So we match at a given scale.
and how should I understand that scale?
Oh, this is just a scale where you do the measurement. It's like the same, the exact same approach as we use at the collector experiment. In fact, for some of the results, you can match to analytical calculations. I will show you some explicit results where we do the matching. Maybe at this point it will become more clear. So, do you have a question? Okay. Yes, you had a question.
So ones that vanish, that are exactly zero, is there a non-perturbative way to see that they had to be zero somehow?
Yeah, the fact that they are zero is a non-perturbative result, right? In the EFT, there should be order one coefficients, they happen to vanish, because there are some hidden symmetries. Okay, we can discuss this hidden symmetries maybe later, but here in my talk, I'm not going to specifically talk about Planck numbers, but after my talk, please ask me why they vanish, and then I can give you an explanation, okay? All right, very good. So now we can match the tidal effects unambiguously by matching the scattering amplitudes computed in EFT to the scattering amplitudes computed in GR. And it's amazing because for GR, for certain processes, we know the scattering amplitude exactly to all orders in G. And in particular, we know it for the case of scattering of different waves of the black hole. So we know a full non-perturbative, we have non-trivial non-perturbative result for the scattering amplitude. And now we can match the EFT order by order and then extract all the Wilson coefficients, understand the tides in a manifestly gauge invariant way. So let me now show you how this program works out in practice. So the warm-up here again, let's go back to our electromagnetic case. Again, let's consider the EFT for neutral atoms or neutral particles. So their action will start with the E squared term on the worldline, and we can easily compute the scattering amplitude. And the scattering amplitude will scale at the polarizability times frequency squared. And this is exactly the scaling that explains the blue color of the sky. So you see that you have more scattering for large frequency. Now, with our EFT that we have here, again, if we just take this worldline operator and compute the scattering amplitude, we can easily just it's a three-level operator. We can easily compute the scattering amplitude. It also will grow with frequency as it should in any effective kind of field theory with irrelevant operators. So this result is very similar to the the blueness of the sky result. But however, the problem is that we cannot make the object neutral in the gravitational sense. So there will always be also the contributions to the scattering amplitude that comes from the point particle part of the action. Just because we always have this minus MDS term. And when coupled to gravity, this will produce scattering of the Newtonian potential and then scattering of the Einstein-Hofmann potential, so the relativistic correction to Newton, and so on and so forth. And these different contributions, they organize very naturally into a post-Minkowski expansion where each diagram has a particular scaling in G, where G is in Newton's constant. And then what happens when we do these calculations is that the nonlinearities of GR, they will generate the mixing between the worldline operators and the loop corrections that come from the mass insertions. And this is precisely the cause for the running of the lot numbers. And you can see that, with this formalism, when we use scattering amplitudes and usual kind of tools of renormalization, we can easily deal with this situation. Now, another important aspect of this calculation is that the dissipation is important. Sometimes we can also have the inverse of dissipation, so amplification due to the effect of superradiance. Because when we scatter a wave of the black hole, the wave can come out with the enhanced intensity if the black hole is rotating. So this is something that we need to worry about as well. So altogether, this whole program, this whole scattering process looks very similar to the Raman scattering, which is intrinsically inelastic, but then it has the additional gravitational complications that have to do with the fact that GR is nonlinear. But in general, yeah, we're just doing the gravitational analog of the Raman scattering. And in dimensional analysis, you can estimate what order, how many diagrams do you need to keep track of in order to match the lot numbers. And then you will see that in general, you will need a 4-loop diagram. So you need to go to 5 post-Newtonian order. So the tidal effects, they show up very, very late in the post-Newtonian expansion. And in general, it's very hard to compute 4 loops. And the first question that I had when I started working on this, can we get some result easy? Well, ideally without computing loops at all. And it turns out, yes, we can. But for that, we have to understand better the other side of the story, which is the scattering in terms of general relativity. So for general relativity, we can solve the scattering problem exactly. And for this, we need to solve the so-called Mikulski-Masser equation, which is just equation that describes the perturbation of gravitational background in the context of black hole perturbation theory. So the cartoon of black hole perturbation theory looks like this. It was done by one of the founders of black hole perturbation theory. So we have a full-fledged GR solution of Kerr or Schwarzschild, and then we send some waves, and then these waves produce some perturbation of the gravitational field of the black hole.
Sorry, Misha, are you
yes.
thinking about scattering over photons or fermions?
So here you can do scattering of fermion of all these different particles, but here I'm mostly going to focus on the scattering of the gravitons.
Okay.
Yeah, unless, I mean, sometimes we can get also result for the photons or, for the scalar field scattering much easier. So I will mention these results, but most of the results that I present will be for the gravitons. Okay, so in full GR, so we need to solve this Tikolsky equation. Tikolsky equation is kind of magical equation because the Kerr black holes, they don't have enough symmetry for the angular and the radial part to separate. But in fact, there are some magical variables called Newman-Penrose scalars for which really the equation separates. And it looks as if you had an extra symmetry for these Newman-Penrose scalars. You have decoupled equation for the angular variables and radial variables, which now you can solve. And so you can solve the, these equations will take a form of Schrödinger equation. So basically you just solve the scattering problem in some particular potential. You can impose the scattering boundary conditions, and you can compute the full scattering amplitude in this case. And this is the result of this computation. You will have some complicated or rather complicated expression, but something magical will happen to this expression if you analytically continue the angular momentum. So angular momentum L is a parameter of your theory. So if we play this Gribov-Rosart trick, if we analytically continue it, then you will see that the scattering amplitude will factorize. There will be a part of the scattering amplitude that will give you the Rutherford scattering with gravitational Rutherford scattering plus post-Newtonian corrections or post-Minkowski corrections in this case that scale like power of g, just usual integer powers of g. And then there will be terms that show a non-analytic behavior for generic L hat, which is the analytically continued L. And they will correspond to the tidal effects, because tidal effects, they really scale general power of L. Maybe the way to understand this is to go to higher dimensions, where you will see that because of the particular relationship between the Newton's constant and the Schwarzschild radius in higher dimensions, the finite size contributions, they will scale non-analytically with G. So they will kind of decouple from the post-Newtonian expansion. And this is something that was utilized before in the off-shell calculations, but here what we have found is that you don't need to go to higher dimensions. You can just analytically continue L and you will get the same result. You can decouple finite size effects from the relativistic corrections. We call this a near-far factorization. And this is something that allows then you to match the tidal effects just from 3-level amplitudes, right? Because then you can focus on the near-zor part that contains all the tidal contributions, and you can match your just 3-level diagrams. Okay, well, there is some subtlety that at some point, as I said, there will be like a non-trivial interaction between the far zone nonlinearities and the near zone that produces the running of the log numbers. And this is something that you will see as the appearance of singularities in the physical limit where n becomes integer. But even if the singularities they happen for a very good reason. And even in this case, you can still use the factorization to extract the logarithmic part, the logarithmic dependence of the log numbers. So we have implemented this program in practice by computing scattering amplitudes at the tree level and matching them to the near zone gravitational wave black hole scattering amplitudes. And we found, we confirmed that the log numbers vanish, log numbers of Schwarzschild black holes, log numbers of Kerr black holes that in general involve, have more complicated operators that depend on the spin. And also we're able to show that the dynamical log numbers are not zero. The one I discussed before, for instance, the ones that correspond to the frequency squared correction to the usual relativistic, usual Newtonian log number. And also there are additional operators that are allowed by symmetry in the case of the Kerr black holes. So they in general run as well. So, and using this factorization, we're able to extract the RG running of these operators. So this is the result that we're able to get without doing the loops. But however, if you want to obtain the finite part, if you want to match also the finite part of the scattering amplitude, sorry, the finite part of the Wilson coefficient, the scheme dependent part, in this case, you need to do a complete calculation. So you need to fully compute the scattering amplitude in AFT and GR. To do that, I teamed up with some of the scattering amplitude experts, Julio Para-Martinez, usually, and we started setting up this calculation. We first decided to focus on a scalar field toy model, and we worked out the scattering amplitude on a partial weight basis, and also along the way we had to come up with a lot of technical inventions in order to simplify the calculations. For instance, we used the background field method to reduce the number of Feynman diagrams describing the post-Newtonian expansion of the gravitational potential of the compact body. But in general, once we implement all these tricks, we use integration by parts, angular differential equations, etc. Then we're able to really compute all the diagrams relevant for the first non-trivial log number matching result. So as I said, we focus on this toy model of a scalar field. And in this case, our worldline action will only have two operators, at least in order. It will have a dynamical scalar field log number and also some gradient type log number. The monopole log number is forbidden by shift symmetry. So these are the only two operators that we'll need for the matching. And we computed, 1 p.m. contribution, 2 p.m., 3 p.m. Something interesting that started happening at 3 p.m. order is that we found some UV divergences that precisely correspond to the counter terms in the form of the log numbers that we need to add to the action to renormalize them. And we have done that. So here you can see the expression for the phase shift at the 3 p.m. order for a scalar field. So in general, there are no divergences for a general L greater than 0. Now for the S wave, there is a UV divergence that also generates some finite logs. And then we can also compare it with the exact scattering amplitude in GR, which at this order gives us obviously a finite answer plus some log that has an explicit matching scale here. And then we match the two, we obtain the full matching of the log number at a given u. So this is how we do this. In this case, we're able to do this analytically. In practice, we can also match to the results of the experiment at a given matching scale. So, right. So this is the first non-trivial matching condition that we obtained completely. And one interesting result that also we're able to obtain is that we're able to show explicitly, like as a result of the full calculation, the log numbers vanish. So in this case, this would correspond to the vanishing of the p wave log number contribution and p wave scattering phase shift. And after that, we extended these results beyond the toy model case. So we're able also to carry out the scattering amplitude calculation for the scattering of the photons. So in the case of the photons, again, there will be some non-trivial matching condition at the 3 p.m. order. So we're able to show that the electromagnetic log numbers are 0, fully without using factorization. Now for the graviton, we at the 3 p.m. order, we don't have counterterms, we don't have log numbers. They will only appear at the 5 p.m. order. So for them, we have the exact factorization results. And then, for higher order, also dynamical log numbers, we also have the results in terms of the logs, leading logs that we obtain from the factorization. So this is the table of the results that we're able to generate with this program of matching scattering amplitudes. But okay, perhaps more interesting comparison is, more interesting application is the neutron stars. For neutron stars, we don't have the full analytic results, but still we can make some predictions. We can understand some interesting phenomena, such as, for instance, the appearance of the effect called the self-running, where if you have a 3-level log number, you can dress it with extra gravitons, and this will generate a running of the log number of the dynamical log number at next to leading order in frequency. And in fact, also there will be universal running from this type of diagrams. So we'll see that higher orders, there are multiple sources of the running in the Wilson coefficients. And this is something that, for neutron stars, we in principle could probe with experimentally with the LIGO data. Any questions? Okay, so perhaps more interesting application is matching of the dissipative tides, because as I said, the most important part of the black hole is that it's inelastic. It absorbs stuff. It will absorb your wave if we shoot it, and we capture this by introducing the inelasticity coefficients. And well, in general, if you want to describe dissipation in this context, the way to do it is to write down an effective worldline action that involves the coupling between the internal composite operators that describe some black hole degrees of freedom and the bulk fields. So for the scalar field, you have a composite mass. For the electromagnetic field, you have a composite dipole. For the gravitational field, you have a composite dissipative quadrupole. And then typically we match the things, the on-shell things such as the absorption cross-section, which is the in correlator. Obviously, it makes it hard, to apply the scattering amplitude technique in that case, but we can do so by using the fluctuation dissipation theorem that allows us to map basically the classical correlation functions to the in-out correlation functions of operators, and now we can use them to, well, we can use the usual machinery of scattering amplitudes to compute those. And we're able to match also the non-elasticity. And what's interesting is that there will also be some UV divergences in the non-elasticity at the 2 p.m. order. And well, you can see their appearance here in this Feynman diagrams. So the leading order term just describes the, let's say, ordinary, the leading order effect of the dissipation. And then there are post-Minkowski corrections to that. And at the two-loop order, there will be both, UV divergence and also some finite log. And this is something that in this case gets normalized by a wave function renormalization. So we can get rid of the divergence. And then there will be some scale dependence of the renormalized multipole, dissipative multipole of the black hole. And we can extract, again, extract RG running by matching this to the BHPT calculation. And we see that indeed, all the finite diagrams, they match exactly, and the diagrams with the logs, the coefficients match perfectly, and we can just, match the two calculations at a given scale and extract the running of the multiples. Yeah, this is something that also, takes place for the neutron stars. I'll skip this at the moment. So the appearance of the running of the dissipative multiples is a very interesting phenomenon that takes place here. You can write down the RG equation for the multiple moment, and at lowest order, so we have this calculation from our scattering amplitude program, and it's kind of interesting to think about the physics that generates this RG running. So in this case, this is because we cannot separate the intrinsic quadrupole moment of a body from the gravitational potential of the same body. Same way, we cannot separate the intrinsic charge of an electron from the vacuum polarization in the QED. So that's why now, well, this is something that gives rise to the RG running here. And in fact, we can now go on to higher orders and we can compute more diagrams, and we can compute this anomalous dimension at higher orders, and we can match them to the full non-perturbative results from GR. And what we'll find is that we can actually extract the exact anomalous dimension of a black hole that will be given by this quantity nu, which is called as a renormalized angular momentum in black hole perturbation theory. Well, this is the formal definition of this normalized angular momentum. So in general, this is just the usual angular momentum L plus some corrections that you can think about as post-Minkowski correction to the angular momentum. So the story is that, well, as you know, for usual case of quantum mechanics, when you solve wave equation in the far zone, you have a solution which is Bessel function as a Newman function that depends on the angular momentum L. Now, if you solve the exact same equations for the Kerr background or Schwarzschild background, you will find that the relevant parameter that will appear in the Bessel function will be this nu. So somehow gravity really doesn't care about the usual angular momentum. It always cares about this strange quantity called the normalized angular momentum. And in principle, we have the expression for it to all orders and frequency. And now we can compute the absorption cross-section in EFT, including higher orders, and compare it to the full GR results. And we'll see that in the full GR setting, the actual dependence of the, well, here gamma is the rate, absorption rate. So the absorption rate will depend on frequency as a power of 2 nu plus 1. So it will be precisely, this nu will control the scaling of your operators that appear in your EFT. So this precisely matches the definition of the anomalous dimension. When I was a undergrad student, it took me a while to understand why it's a good idea to resum the logs in the anomalous dimension. But here, by comparing EFT result with the full GR result, you can see very clearly that the reason is that you always have this non-analytic dependence on frequency. You always have frequency to the power of frequency. And just when you Taylor expand, you get the logs. But in general, you don't have to Taylor expand. And the usual kind of RG technique basically just gives you this answer right away. Okay, so we can obtain the exact anomalous dimension for the black hole. So why this result is interesting? So it's interesting from the conceptual point of view because we don't have that many systems with the exact solution to the RG equations. But most importantly is that actually we can use this result now to improve the modeling of the waveforms. So we can resum the logs that appear in the waveforms. And this is because, in fact, the black holes, the anomalous dimension of a black hole to a large extent coincides with the anomalous dimension of any other object. And this is something that just follows from the equivalence principle. So in this EFT for gravity that I talked before, we have this one body sector. Okay, we have this let's say linear order action in the one body sector that involves the point particle, the mass monopole, some spin dependent terms, and then the dissipative quadrupoles plus the log numbers, etc. Now, if we want to write down the action that describes the emission of radiation from a binary, this action will take the exact same form. You just have to replace the mass with the energy of the binary. The angular momentum will be the same because this is something that defines the angular momentum. And then also you'll have a universal coupling between the multiple moments and the gravitational field that always comes, from quadrupoles that are coupled to the electric and magnetic gravitational fields. So these are the same actions. Right? So now let's draw diagrams that describe the absorption of waves by a black hole and the emission of waves by a binary. And you will see that these diagrams, when you include the interaction of the radiation with the gravitational potential of the source, they will look exactly the same. Right? So this diagram tells you how the gravitational waves coming to your black hole, they get scattered by the potential and then absorbed by the black hole. Now this diagram tells you how you emit the radiation from a binary, and then this radiation gets scattered by the potential. So kind of the radiation goes in different directions, but the diagrams are exactly the same. And this is something that comes basically from the equivalence principle, right? From the same structure of the actions in this case. And in fact, people before, they have computed the anomalous dimension of the multiples of the binary in a linear order. It precisely coincided with the black hole Raman scattering result. And this is precisely because the diagrams are the same. So in fact, now, since we can resum these diagrams for a black hole, we can also resum the same diagrams for the binary. And by the way, note on the nomenclature. So the most Newtonian people, they call this corrections UV tails. So sometimes there are also IR tails, but this is the kind of word that is attached to just UV divergences that come from the insertion of the mass terms in the effective action. Okay, so once we have the full anomalous dimension for a black hole, we can actually take a look at this and try to understand what pieces of it are universal and what pieces are not universal. And you can very quickly convince yourself that the terms that do not depend on spin, that all mass-dependent terms through the order g to the 2l plus 1 are universal because they describe by the same kind of diagrams where you have the coupling between the gravitational waves and the mass insertions. Also terms that are linear order in spin are universal. But then, however, there will be some diagrams at order higher than g. They will start at the order g to the power 2l plus 2 that will be non-universal. And there are several sources of non-universality. Basically, because at some point you will have log numbers that will start contributing to the anomalous dimension. Also, you will have some spin-dependent operators that will start contributing. And we have the no-hair theorem for black holes. So that's why the spin action for the black hole is very different from the spin action from the binary. But you can easily kind of identify the universal and non-universal pieces. Okay, so once we have this universal result, now we can check whether this matches the calculations that I showed before. In fact, in the quadrupolar sector, just recently there were calculations where people pushed this anomalous dimension to higher orders, to the 4 p.m. order. And in fact, our formula coincided precisely. It reproduced all the low order results and also predicted a new 5 Post-Minkowski result. And the predictions are even more interesting in the case of the octopole. So octopole radiation, in this case, basically only leading order result was known, which our formula reproduces, but then it gives the answer also to highest orders all the way up to the 7 post-Newtonian order. And in fact, this anomalous dimension is universal, just again, because of the equivalence principle, and basically any object, so binary, neutron star, Bose star, anything, will have the exact same anomalous dimension. Okay. And once we had this understanding of the resummation of the anomalous dimension, now we can actually apply this to the gravitational waveforms. And well, as you know, there were many decades of the post-Newtonian calculations where people improved order by order in the waveform. And in the past, they have already identified some enhanced contributions due to IR effects, basically due to the Sommerfeld enhancement, or and they realized that it's a good idea to resum those. So there's already some resummed IR part. And this resum part depends on the usual angular momentum. But as we learned, gravity doesn't care about the angular momentum. What it cares is this renormalized angular momentum. So basically, the resummation of all UV corrections to the usual post-Newtonian result will happen if we just replace in these formulas, in the infrared formulas, infrared resummation formulas, if we replace here the angular momentum with the renormalized angular momentum nu that I introduced before, that precisely captures the anomalous dimension. So then we have a new type of resummation that resums both IR effects and UV effects, so IR logs and UV logs. And we went out and checked explicitly whether it matches the post-Newtonian calculations. We took the state-of-the-art 4 p.m. result by Blanchet and collaborators that has a lot of, pi factors come from the IR terms, so this is Sommerfeld factor, and then we have these logs that come from the UV diagrams, from these UV tails. And after we apply our resummation formulas, you see that basically it resums all possible pi factors, so it resums all the IR terms, and also it resums all the UV terms. So you see all the logs disappear except for one. Well, this log corresponds to something that's called the tail of the memory effect, so it's a source specific, so we cannot quite resum this, but otherwise we resummed all of them. And you can see that indeed, using scattering amplitude seems to be useful in terms of the waveforms. So we have simplified the waveform tremendously. Obviously, our formula also predicts many new logs that have not been computed before that are now resummed. And okay, we're working now on the application of this resummation formula in data analysis. And speaking of data analysis, in the dying minutes of my talk, let me present you one particular result, which I find interesting, which is the search for exotic compact objects using the EFT. So let me just kind of switch gears completely and go to the beginning of my talk when I talked about the tidal deformations and tidal heating. As I said, there are big efforts to understand the equations of state of compact bodies using tidal deformations, using conservative tides. But you can also do similar search by utilizing the tidal heating effects. You can use EFT for that, because basically before we were matching the EFT calculations to jar calculations, but now we can match the EFT calculations to the data itself, and we can try to do a model independent search for exotic compact objects in the form of that produce anomalous tidal heating effects that will lead to dissipation of gravitational waves. So we took these EFT expressions for the dissipative multipoles and calculated the waveforms for them and reanalyzed the LIGO Virgo KAGRA data, and we're able to set very strong constraints on these EFT coefficients. They're constrained to, let's say, order 20, which maybe doesn't seem like a big result, but if you convert this into the actual amount of the flux that we constrain, so we constrain the amount of the flux absorbed by the compact body, and this is something that is constrained to the thermal level. You see, it's constrained to the 2 times 10 to minus 3. So we have a per mile precision kind of constraint on the amount of radiation absorbed by compact objects. So we think that this is something that shows you that EFT can also kind of be useful for phenomenological applications as well. All right, with that, let me summarize my talk. Well, basically the main summary of my talk is that if you want to understand classical jar, you have to use quantum field theory and scattering amplitudes. And that's the only way that is kind of clear and you will not make mistakes. So I know this sounds crazy, but this is true. And this application of scattering amplitudes allow us to resolve all these ambiguities with the definition of Love numbers, with the matching of Love numbers, and also make some new predictions for the waveforms, in particular resum all the universal logarithms in the waveforms. And with that, we hope that there will be more EFT results when applied to the gravitational wave science in the future. I guess I'll stop at this point, and then thank you for your attention and take your questions.
I'm a bit confused. So because you're trying to, what does this buy you on top of trying to solve the Tucholsky equation directly?
Very good. Excellent point. Okay, so Tucholsky equation can only, you can solve it only for a few regimes. Okay, you can solve the scattering problem, but you cannot solve, for instance, the full gravitational waveform, right? If you have a perturbation which is big, right? So for instance, you can use it to compute the waveforms in the regime of the extreme mass ratio, but not in general. Now with these tools, with the EFT, you can use the Tucholsky equation as a tool for the matching. And then in that case, you can have a computation for generic masses. You can have computation for generic situations, right? So we use the Tucholsky equation here only as a tool for the matching, because it gives us the exact result for a few select problems, such as the extreme mass ratio waveforms and also the scattering of gravitational waves.
The amount of terms you have to keep depends upon the mass ratio, or you can just exactly resum everything.
Yeah, well, here exactly. We basically in these results, I never had to assume that the masses are
Some number.
different. Yeah, like they could be order 1. These predictions that we generated for instance, for the dynamical of numbers, you can use the same waveform prediction for any masses.
And then you have another prescription to join the EFT onto something once you get to the ISCO or something. Because you had 3 different EFTs, right? And
yeah. So the one EFT that we use in the end is the radiational. If you want to compute the waveforms, okay, the way you do it is you kind of integrate out these other 2 EFTs. So you compute the one body potential modes, you compute the binary potential modes, and then you integrate them out. And in the background of those modes, you compute the radiation. And it is this last computation then you can use to match the data.
What's the experimental status of constraints on Love numbers, let's say for neutron stars, and how well do they, let's say, tell us what the equations of state look like?
Yeah, well, I feel like right now, since there was only one event, well, I should say these constraints are kind of interesting, but they're not great. Okay. So I feel like the physical interesting regime is when the Love numbers are around, let's say 10 or 20. So right now, as you can see, it's like 1000. And more or less, also you can do a search for exotic compact objects based on Love numbers, and you will get a figure roughly the same, like less than 1000 or something.
But were there other neutron star mergers that we saw since then?
One.
Oh, that's the only one.
Yeah. Unfortunately, that's the only one that they had.
Are these anomalous dimensions that you mentioned some kind of critical exponents in some system with a scale symmetry or something like that? What is the theoretical structure of them?
Yeah, so they precisely correspond to the scaling dimension of well, in this case of some operator, this dissipative operators.
The scaling dimension usually refers to a system with a scale symmetry. So what system is that?
Well, here we don't have quite scale symmetry. Yeah, we have explicit scales always. But here, what the anomalous dimension does, controls the scaling of the, let's say, multiple moments with frequency. Somewhere here.
But if you have explicit scales, why do you get these power laws? And I'm kind of confused about the answer, actually. Like, usually if you have exact power laws with interesting exponents, you have a scale symmetry. If you don't have a scale symmetry, you would not expect power laws.
Yeah, well, in this case, we don't have an exact power law. Because you see, we have some power law dependence on a parameter that depends on the frequency itself. So this is kind of generic situation in the field theory that has mass parameters, right?
I see. Nu itself, nu is a function of omega.
Exactly. Nu is a function of omega. Yeah. So nu is L plus some Taylor series in omega.
I see.
Right. So it's just like a usual anomalous dimension of usual field theories with scales.
If there are no more questions, let's thank Mikhail again.
Very impressive.